we can use radioactive decay to date things. One way we can do that is for living things or things that were once alive is by using carbon-14. So up in the atmosphere, nitrogen gets turned into this radioactive carbon-14 because of cosmic radiation. That carbon-14 then also decays, and you get a balance of carbon-14 in the atmosphere that's relatively constant. So you have basically the same amount of carbon-14 in the atmosphere all the time. Of course, we get our atmosphere by eating plants. We get our carbon by eating plants, and the plants get the carbon from the carbon dioxide in the atmosphere. So a certain fairly steady fraction of that carbon dioxide in the atmosphere is carbon-14, and so the plants have about the same fraction of carbon-14 in them as there is carbon-14 in the atmosphere, and since we eat the plants, we have about the same fraction of carbon-14 in us. Now, while we're alive, we're always eating new plants, and so if any of our carbon-14 decays, then our body is always rebuilding and replenishing, and so we have basically that constant fraction of carbon-14. But so we go along and we have sort of a constant amount of carbon-14 until we die. So when we die, then we stop taking in new carbon-14, and the carbon-14 we have starts to decay because it's radioactive. So what we can do is we can say, all right, well, we find something dead, and we measure how much radioactive carbon does it have now. So how much of it has been depleted, and then we can measure out how long it's been since the time of death. Okay, so that's how we can date when something died using this carbon-14 dating. Now the half-life is 5,730 years, so if you wait that long, you only have half as much carbon-14 as you had. If you do that 2 or 3 times, you start to be, you're going to have a very small amount of carbon-14 left, and it's going to be hard to accurately detect just what fraction has decayed. So this is good for dating things for a few thousand years, no problem. Okay, so let's see. We know that there's only 15% of what we started with in this thing. So we know our model is that dy dt, the rate of change, should be proportional to the rate. After all, these radioactive atoms each have the same chance of being able to become normal in a given period of time. And since that's our differential equation, we know that our solution is that the amount at any time should be the initial amount times e to the RT. Now in our case, we know that 15% of the radioactive carbon has decayed. That means that 85% of what we started with is still there. So if we started off with 100% or 1, now we have 0.85. So if I solve this for t, I could take the natural log of both sides. The natural log of 0.85 would be the natural log of e to the RT would just be RT. So the time since this thing died would be the natural log of 0.85 over r. But I need to know r in order to figure out what the time is. I can get that from the half-life because I know that however much you start with, if you wait 5,730 years, then you'll have y naught e to the r times 5,730. But in that time, you will only have half of what you started with. That's the half-life. So the initial amount cancels on both sides, and I have this equation that I can use to solve for r. So I have the natural log of 1/2 would be the natural log of this side, which is r times 5,730. So r is actually the natural log of 1/2 all over 5,730. I can now plug that in so I can figure out what t is. I have the natural log of 0.85 over the natural log of 1/2, or 0.5, over 5,730. Since I have this tiny fraction downstairs, why don't I multiply top and bottom by 5,730 just to clean it up a little bit. Multiply the top and the bottom by the same number. I end up with 5,730 times the natural log of 0.85 all over the natural log of 0.5. Now we can get an approximation, figure out how old that object is. Let's start off by taking 0.85. Let's find its natural log, and then I'll divide by the natural log of 0.5, and then just multiply by 5,730. And we get 1,343 years, about. 1,343 years as the age of this object.